Welcome to Brain Vision.
Okay, so in this question, we have a string that is vibrating. The mass of the string is equal to 4.80 grams, which of course is equal to 0.00480 kilograms, which is what we'll end up wanting to use when we actually start doing calculations. The length of the string is 2 meters, 2.00. And the tension applied to the string is 48.0 newtons. And then the last bit of information that we're given is that it's vibrating in its second normal mode. So n is equal to 2. And the string is fixed at both ends. So there's going to be nodes at either end. So from here in part A, we're supposed to figure out whether or not whether the wavelength caused by the sound wave by the string vibrating is larger than the wavelength of the string it's vibrating itself. So we want to find the wavelength of the sound in air and compare it to the wavelength of the string itself. So there's kind of a bit of a two-step process here. The first thing that we want to do is we want to figure out a relationship between the wavelength of the string's vibration and its length. So we're told that it's fixed at either end, which means that it has to have a node at both ends. And then in its second mode of vibration, which means that we're going to have an extra node in the middle here. So its vibration is going to look something like this. Which of course means that we have a full wavelength along its length. So L is going to be equal to lambda. And then the next thing that we can do, since we already know, how long the wavelength of the string is, now we want to figure out the wavelength of the sound wave. So what we want to do is we want to figure out what the frequency of the string is, because the frequency of the string is going to be the same as the frequency of the sound wave. So and in this case, because we're dealing with a physical string, we know that V is going to be equal to the square root of tension over mu, which is just the string's mass divided by its length, which means that we can rewrite this square root as T times L over M. And that ended up a little bit cramped there, but so we're going to go ahead and rewrite this. And of course, we know that lambda is just equal to L, as we've already established. So this makes our formula for frequency equal to the square root of TL over M, all divided by L. And we're all given all of that information. We're given all of that information straight away from the beginning, so we can go ahead and calculate the frequency. So the formula, when we start plugging in values, ends up becoming 2, or I wrote it backwards when I did my homework, but if we go with tension first, it'll be 48.0 times 2.00 meters, and that's divided by 0.00480, because we had 4.8 grams for the mass, and then we have the length one more time, which is 2 meters. And if you calculate that out, you'll get that the frequency is going to be 70.7 hertz. And we can use this to figure out what the wavelength in air is. So we're assuming just that the speed of sound in air is just the normal 343 meters per second. So we can say that the wavelength in air, I'm going to say that's lambda air, it's going to be equal to V air over F. And then, of course, F is the same as it is for the string. So V air is 343, as I just said, and then F is 70.7, which we just calculated. And if you plug that in to your calculator, you'll get that the wavelength in air is 4.85 meters, which, if you compare to the wavelength of the string, which is only 2 meters, we see that the wavelength of the sound wave is in fact longer. So our answer for part A then is that the wavelength is larger in air than on the string. So that's our answer for part A. And then in part B, we're asked to figure out what the ratio of the wavelength in air is to the wavelength in the string is. So there's two ways to do this. It doesn't specify whether it wants a number answer or whether it wants a symbolic answer. So I'm going to go ahead and give both. The number answer is pretty straightforward. We have the wavelength in air and we have the wavelength in the string. So the ratio is lambda air over lambda, and that's equal to 4.85 divided by 2. And if you plug that in, you get that the ratio is 2.43. So that's our numerical answer. But if we want a symbolic answer, which I think is probably what they're going for, but it's not very clear, we can say that lambda air over lambda, we can substitute those for their respective velocities over frequency, coming from the formula lambda is equal to v over f. So v air divided by f, so lambda air is equal to v air divided by f, and then all of that is over v divided by f. And of course, the frequency is the same for both of them, so we don't need to specify for those, and they end up canceling. And then our ratio ends up being v air divided by v, which I think is this is why I think they were asking about a symbolic answer, because this is actually a very simple relationship and shows, how the waves are related. It is just by the properties of the medium. So the wavelengths are related by how fast the wave moves in air over how fast the wave moves in the string, which I think is very, interesting, very cool. So yeah, I think this is what they were going for, but either way, if they wanted a number answer or symbolic answer, you have that there all laid out for you. So yeah, that's how you do this problem.